Hello everyone, I'm Ilkin and my group mates are Chase, Dominic, and Shirin, and we will be talking about photorealistic text-to-image diffusion models with deep language understanding. We will start with the introduction, and then we will talk about the motivation behind this paper. We will discuss the contributions, we will talk about the contributions and then discuss the evaluations and the results, and we will end with the conclusion. So text-to-image task, as we all know, is a task where we give the text as the input to the model and a model that generates us corresponding image from that text image. As we learned from the class, generative adversarial networks, VQ, variational autoencoder transformer-based methods, autoregressive models, and the diffusion models are great for this task. And we know that diffusion models outperform GANs for image generation in fidelity and diversity without the mode collapse issues and also the training instability. We also know that cascaded models are great for generating high resolution images, which is used in the proposed method. There has been great work done for this task, and some of them are DALL-E 2, Glide, and XMC GAN, but all of them have some drawbacks. And in the paper, it's mentioned that DALL-E 2 is complex for needing to learn the latent prior, and Glide is insufficient when it comes to image fidelity, and XMC GAN, it has a relatively small encoder, which causes it to perform worse than Imagen. So in this paper, they're proposing a simpler model that doesn't need to learn the latent prior and perform better than the previous work. So Imagen is able to generate these images when we give the text inputs. Here are some examples. For example, teddy bear swimming at the Olympics 400-meter butterfly event, or if we were to ask the model to generate an image for a cute corgi lives in a house made out of sushi, it's gonna generate a similar image. And the way they achieve this is by combining a large transformer language model to understand the text and diffusion models to generate the high fidelity images. And the goal of the paper is to achieve a degree of photorealism that hasn't been achieved before and a deep level of language understanding. So when we look at the previous work, especially DALL-E 2, we see how it fails in some cases. One example is here, us asking the model to generate a Greek statue of a man tripping over a cat, and DALL-E 2 generates some images where the man is patting the cat or the cat is on the back of someone. But with Imagen, we're able to generate images where the man is actually tripping over the cat. Another example would be color to object match. So if you were to ask the model to generate an image for a black apple and a green backpack, DALL-E 2 is not able to match the color to the object, and Imagen is able to do that perfectly. In the paper, they show that the large frozen text models that are only trained on text data are effective for text-to-image generation, and text encoder size is key to improving image quality. In the paper, they propose a simpler and efficient architecture, which is efficient UNet. We'll be talking about this one. And they also introduced dynamic thresholding for generating photorealistic images. They claim that the proposed method is the new state of the art for COCO with good text image match, and it outperforms all other work on a new benchmark, DrawBench, which has challenging and comprehensive samples. The Imagen consists of a frozen text encoder and a cascade of diffusion models. In the first diffusion model that we give the text embeddings to is a traditional guided diffusion model with classifier-free guidance and dynamic thresholding. And then we have two super resolution diffusion models that upsamples the 64 by 64 image to 1024 and 1024 image. And Chase is gonna get into more details of the model.
So now that we've given you guys a overview of the model, we can first talk about the text encoder that's used in the model. So as we've learned, robust text encoders are very important to have good image generation. The better understanding of the given language we have, better images we can generate. So Imagen actually compared BERT, T5, which is their own model developed by Google, and CLIP. And they compared all of these as frozen text encoders. Early on, they actually ruled out BERT as a good model because T5 and CLIP ended up vastly outperforming it in FID scores. But with T5 specifically, they found that scaling the text encoder would actually give them large improvements in their text-to-image generation capabilities. And this actually allowed them to choose T5 over CLIP because as it performed the same in FID tests, it actually won in human evaluation, which we'll see later in this presentation. In this scaled T5 model, they ended up referring to as T5 XXL. And to the right, we just have a brief overview of what an encoder-decoder model is, just as a refresher, but we all know how those work by now. So now we can talk about what's different about T5. So traditional BERT style models, they give you outputs with class labels or sequences of tokens. However, T5 gives you readable text. So this is better for a human understanding of what's actually happening. The model doesn't actually care one way or another whether or not there's readable text output, because of course we're just using text embeddings, but T5 is special in this way. And T5 is actually useful for translation. So in this case, we're doing English to German, grammar checking, determining whether or not a sentence is acceptable. So here we have the courses jumping well, and obviously that's not really an acceptable sentence for grammar in the English language. And then we can also do sentence similarity, so comparing subject and content of an two sentences. And lastly, summarization, which is pretty obvious. And for these T5 text embeddings that they're receiving, they're going to actually use cross-attention in the diffusion models to use the guidance of the text embeddings. And next we can talk about the second main contribution in this paper, which is the efficient U-Net. So this efficient U-Net is actually only used in the super resolution models, not the normal text to diffusion model. And what's special about it is it provides better memory efficiency, faster sampling, and faster convergence than a traditional U-Net. So the way that they get better memory efficiency is they actually focus most of the parameters in the U-Net in the lower resolution blocks. So they don't actually specify which blocks they consider lower resolution, but I think we can assume it's in the 64 to 16 pixel block range. And the reason that this helps is because they're allowed to have wider blocks that are less deep in this lower resolution range, so they get higher throughput in the model, but they don't have the memory efficiency penalty that would be that would go with a really wide and really deep block, which would be up here with the 256 and 128 blocks. So to get faster sampling, they actually realized that in the U-Net you can flip the order of the convolution and up and down sample operations to get 2 to 3 times faster sampling. I'll explain this with the picture on the next slide, but just keep that in mind for now. And then lastly, for convergence, they realized that the lower resolution blocks didn't actually have enough ResNet blocks or layers in them. So instead of having 2 to 3, they actually upped it to 8. And in addition, they scaled all of the skip connections, which we are familiar with are these, by 1/√2. And that's actually an increase in length. And this, as I said, resulted in a much faster convergence. So we can see with this graph here, they're getting the same, or actually a better FID score in half the number of training days for their new efficient U-Net compared to the original U-Net. And so now I'll give you a better explanation of what the change in convolution order really means. So on the left, we have the traditional U-Net, where we have convolutions followed by downsample operations. And in this case, we're going to have 3 of those joint operations until we hit our latent space. And on the way back up, we're going to have an upsample followed by convolution. Again, we have 3 of those operations until we hit our original or our new image size. So what they propose instead is that we reverse the operations on each side. So now we have downsampling and convolution following that. So we have 1, 2, 3 operations in this new ordered pairing. And then we reach the latent space. Keep in mind, these black arrows are not actually denoting any sort of transformation on the data. This is simply saying we're arriving to the latent space without any operation. And on the way back up, again, we're flipping the operation. So instead of upsampling first, we're upsampling after the convolution. They don't really give a reason as to why this increases sampling speed, but again, it does give them a 2 to 3 times increase in sampling speed during inference. And lastly, for the efficient U-Net, I'll just give you guys an overview of what the block.
Generated images, self-driving cars, augmented reality, virtual reality, it's all around us.
They're not very different than what we've seen previously, but in this case, they actually determined that the convolution and self-attention blocks can be optional, and some of the downsampling and upsampling blocks However, the conditional embeddings for the text embeddings are going to be required, as well as having some in ResNet blocks. And in this case, like I said, they'll have 8 in the lower resolution blocks, but they don't specify how many they have in the higher resolution blocks. And again, for the upsampling block, we're really seeing the same thing. They changed the ordering a bit. They don't give an explanation, but of course we have our skip connections from the D block to the U block, as we saw in the previous slides. So now that we've covered the efficient unit, I'll do a quick overview of the diffusion model. It's pretty similar to what we've seen before, but it's still worth covering. So in the forward process, they're going to have this Gaussian process defined by Markovian structure. We've seen this many times before. This is a definition of constantly noising an image from 0 to capital T until we reach our final distribution of normal distribution of noise. So in their equation, they define these alpha and sigma parameters, and they kind of just say that they are parameters that shape the noising process. And they define sigma squared T given T minus 1 to be this equation that takes advantage of the signal to noise ratio of the image given by lambda here. They don't really give a lot of information as to how they chose these parameters, but they are responsible for the amount of noise added at each time step. And again, we're going to continue this process until we reach the normal noise centered at 0. And the reverse process is the same as many times we've seen before. So they're going to define a denoising model, xat theta, and train it using weighted square error loss with KL divergence. And that yields our normal error equation we've seen many times before. And of course, we're going to be denoising this middle equation here, which represents our ZT at any time. And we're going to obtain ZT minus 1 through our denoising process. And of course, we're going to go from our final or our noise image back to our original inputs. And lastly, we can talk about sampling. So they determined that they would use the sampling method given by the DDIM paper, which we heard about in the stable diffusion presentation. This formula can be defined as above. We're having our alpha and sigma noise to ratio parameters, or sorry, signal to noise ratio parameters once again, and they're going to be applied to our denoising model to help get ZT minus 1 from any given ZT. So one last thing is I've been talking so far about this diffusion model as if it was using classifier guidance. However, they use classifier free guidance in this paper, and this will allow them to define some new denoising model, which I'll discuss in a second. Just to recap though, classifier guidance, as we know, increases sample quality, yet it has a trade-off in diversity and requires an extra pre-trained model to be used, which isn't really very beneficial. So classifier free guidance instead will use a pairing of conditioned and unconditioned objectives. And in this case, they're going to drop 10% of their conditioned objectives to perform their classifier free guidance. So they will actually give a new definition of their denoising model given here. The important part we want to look at is actually this epsilon tilde theta variable. So this is actually what controls our classifier free guidance. On the left, we have our conditional guidance. On the right, our unconditional guidance. And each one of these is governed by a weighting factor omega. So we can note that setting omega to 1 will actually leave us with plain classifier guidance because we will completely lose our unguided part of the equation and we're left with the guided part. And finally, we can say that setting omega greater than 1 strengthens the guidance effect. And this can have a couple of effects, positive and negative, which Dominic is going to take over and discuss for you guys.
Right, so classifier free guidance is great, but it is by no means perfect. So say we want to generate a photo of an astronaut riding a horse at these lower weights. The images look pretty good. They're kind of dark, but the horse and the astronaut are still there, so it's okay. But as you increase the weights, the images tend to go to black and they just oversaturate. Which is obviously not what you want when you're trying to generate an image. The reason why this is happening is because the pixel range is supposed to be between -1 and 1. That is the range used during training. However, during inference, when the pixels during each denoising step go outside of this range, you get these just black images. So the authors propose 2 solutions to this, which they call static and dynamic thresholding. So the first solution we'll go over is static thresholding. Basically, all this is clipping each denoising step to be within the allowed range, -1 and 1. This is better than doing nothing. because instead of having these exploding pixel values that will be, going very negative or very positive, that are just way outside the allowed bounds, you are now at each denoising step cutting them so that they can be no bigger than -1 or 1. So while this is better than doing nothing, it is still not perfect because the pixel values tend to aggregate at the edges, and there's nothing really pushing them inward. The reason why it is better though is because since they're at the edges, there is a chance that maybe the pixel values will move inward, and you won't get such saturated images. So the other solution is dynamic thresholding, and this introduces a new term S. So to find S, you first have to take the absolute value of each denoising sample, and then from there you turn the pixel values into a distribution, and you choose some nth percentile pixel value. The authors don't specify how they determine the percentile, just that you choose some percentile, but whatever percentile you choose, the pixel value at that percentile becomes S. So then from there, you clip the current denoising sample to be within the bounds of -S and S. And then finally, you divide all of the pixel values by S. And what this does is it actually pushes the pixel values inward rather than just what static thresholding was doing, holding them at the edges. And as you'll see, this helps a lot, and it actually stops the saturation altogether. So let's take a look at some qualitative results. So for static thresholding, at the lower weights, you'll see that the background is no longer saturating. We actually get a background in these images now, which is great. However, at the higher guidance weights, the background is still going to black, which is unfortunate. However, the one good thing about it is that we are now getting the horse and the astronaut, which is the main focus of the image. So, even though the static thresholding isn't perfect, it does still help with producing good samples. Now let's look at dynamic thresholding. Just like static thresholding, dynamic thresholding at lower weights produces great images. And then even as we start to increase the guidance weights, the images are still great. There's no more saturation. We get the full background. We see stuff, we get some greenery and some skies. And then we are still also getting the astronaut and his horse. So this is obviously a huge improvement over what we were getting before with no thresholding, where the images were going to black. So they plotted these results. They did the classic FID versus clip score plot, and so both thresholding techniques have a similar FID score, meaning that they produce about the same fidelity images. However, the clip score of dynamic thresholding is better. So the dynamic thresholding is able to produce more varied images. So that is it for the thresholding techniques. Let's move on to upsampling. So Chase had mentioned upsampling in the efficient UNet before. The authors do the upsampling the same way that everyone else does it. They use the 64 to 256 to 1024 upsampling pattern. And then at each upsampling step, they use a text conditional super resolution diffusion model. The reason why they do it, again, is the same as everyone else. Upsampling just helps with generating higher fidelity images. It generates higher fidelity images. The one interesting thing they do with upsampling, though, is that they use something they call noise level conditioning. And what this does is it just generally increases image fidelity, as well as reducing any kind of artifacts that are left behind by upsampling. So this noise level conditioning, what it is before the current image is upsampled to a higher resolution, they add some Gaussian noise to that image. This Og level is representative of the intensity of that noise, and that noise is the same noise that is used to completely noise the images during the noising process in training. So during training and inference, the noise level conditioning is handled a little bit differently. During training, you choose a random augmentation level, and you apply that to both steps of the upsampling, and you don't change it. And so what this does is it allows the model to learn a variety of different augmentation levels, because each individual image will get a random one, so you'll be able to see a lot of different augmentation levels. During inference, the augmentation level, or multiple different augmentation levels, will be applied to the same image, and whichever augmentation level ends up producing the best result is the one we go with, and it ends up being the final image. So with that, my turn is done. I will pass it off to Shireen to talk about the experiments and wrap it up.
Hi everyone, I'd be talking about
Generated images, self-driving cars, augmented reality, virtual reality, it's all around us.
the result, the impact of some design choices, limitation, and lastly, the conclusion. Now, this table here shows the FID scores of the Imagen model on the MS-COCO evaluation set, where from our previous presentation, we have already learned that lower the FID score is, the better the model's performance is. And we can see from here that Imagen is receiving quite a good score, and which means a good performance while compared to other diffusion or GAN-based models. On the other hand, this table shows the human evaluator's preference of the Imagen model, where the first row reports all of the text prompts of the MS-COCO dataset, and we can see that Imagen is receiving 39.5% preference in terms of photorealism, which shows somewhat good quality of the model's performance. However, in the second row, the authors have actually filtered out the people-related prompts from the MS-COCO dataset, and this actually boosts up Imagen's performance up to 43.9%, which shows the limitation of Imagen in terms of generating images with people. However, in the alignment column, we can see Imagen is receiving the same preference as the original images in both the original and the filtered dataset, and which actually means that Imagen is performing quite well in terms of generating images that are perfectly aligned with the MS-COCO text prompts. Now, even though MS-COCO is quite a standard benchmark to evaluate such models, it still has a limited set of text prompts, which is why it is not readily able to provide insights to different abilities of the models, which is why the authors have come up with a comprehensive set of text prompts and named it as Drawbench. It has 200 different prompts across 11 categories, and this table here shows all those 11 categories. What these categories do is basically they check the model's ability to generate images based on prompts in each of these categories. And lastly, the human evaluators are actually used to evaluate or give their preference of the generated images on each of these categories. Now, these are some results of the Drawbench dataset, where the two parameters are alignment and fidelity, where alignment shows how similar the generated image is to the given caption, and fidelity is the same parameter of MS-COCO, that is the photorealism. They have just changed the name. Now, in these cases, we can see that Imagen is receiving really high preference in terms of both alignment and fidelity in case of the DALI 2 model, and the same phenomena is seen in case of Glide as well, which actually shows that Imagen is performing way better when given comprehensive set of text prompts. Now, I'd like to show some examples on the colors category, where the given prompt is a yellow book and a red vase. And from the images generated by Imagen, we can see that all the images are perfectly aligned with the text prompt, as well as maintaining good photorealism and diversity. However, when we see the results of Glide, we can see the pictures are lacking in diversity, even though they are aligned with the prompt. And also the top two images are lacking photorealism as well. However, in case of the images generated by DALI 2, we can see the images are not even aligned with the text, as the vases are yellow and the books are red. And this limitation was mentioned in one of our previous presentations, that DALI 2 lacks the ability to bind attributes to certain objects. However, when seeing all these images together, we can clearly see that Imagen is performing way better than the other two models. And the same thing is seen in case of another example as well, which is the ability to generate text, where the prompt is a storefront with text to image written on it. And we can see from this result that Imagen is perfectly doing that. However, the DALI-2 model is lacking the same ability because it does not generate any part of the given text. And the same thing is seen in case of Glide as well, which actually shows that DALI-2 and Glide, both of these models are lacking the ability to generate images with specified text prompt. Now, why is Imagen performing so well? There are some design choices that the authors made throughout their process, which is actually giving this better performance. The first one being the scale of different models. This diagram actually shows the result of scaling of the diffusion model from 300 million to 2 billion parameters. And we can see that even after changing the parameter size up to that much, the performance of the model remained almost the same, which shows that actually the impact of scaling on the diffusion models does not really affect the model's performance. However, when the same thing was done in case of the text encoders, we can see as the size increased from small to 2XL, the model's performance grew extensively. And from this, the authors are actually saying that large text encoders are way more effective in this kind of task than large diffusion models. However, in this black dashed line, we can see that CLIP is achieving the same result as the T5-2XL model. So the authors wanted to see which one the human evaluators are preferring more on the drawbench dataset. And this diagram actually shows that T5-2XL model is more preferred by the humans in terms of alignment and fidelity. So from here, the authors are actually hypothesizing that the bigger language models are more able to encode the compositional text prompts better than CLIP-based models. Another of their design choice was to use cross-attention for the text conditioning method, and the effect is seen by this diagram here. And from here, we can see that cross-attention is performing way better than other pooling-based methods. And this is due to the fact that cross-attention actually allows the model to dynamically weight each part or certain parts of the text and image at each timestamp. However, the pooling-based methods actually used a fixed representation of both the text and images, which is why cross-attention is able to generate more accurate images. Now, even though Imagen has its own set of strong key points, it comes with its limitations as well, where the first one is the dataset bias. Since all these text-to-image models are specifically reliable on large-scale dataset, most of these datasets are uncurated and web script, which is why there's often a social and cultural bias portrayed in the dataset. And when you train a model based on those datasets, the same bias is seen in the images as well. The second issue is the poor performance in generating people, the result of which we actually saw in the effect in the MS-COCO results. However, now, if you want to generate some people based on such biased dataset, it could be quite triggering or harmful for some socially minor group, since those biases are portrayed in the images. And this brings a huge ethical issue. However, why this poor performance was happening is not explicitly mentioned by the authors. The third limitation is the scalability issue. Since this model is really huge, it is not suitable for end users or edge devices. And lastly, even though the drawbench dataset is a new evaluation method, it's quite limited in terms of size, as it only has 200 prompts. And also, other than some categories, most of the prompts are done by the authors themselves. And if they were outsourced, it could have been a more robust dataset. So to sum it up, Imagen actually shows the effectiveness of using large text encoders over using large diffusion models, which brings us to one research direction of having even bigger language models. Secondly, they also shown that text embedding with cross-attention is a better method of text conditioning. And also the dynamic thresholding method is responsible for creating more photorealistic images. Moreover, they have also introduced the efficient unit network for the supersampling task, and they have shown that it is way better in terms of both convergence as well as memory efficiency. And lastly, they have also introduced the drawbench, which is a more robust evaluation method than the other methods of evaluation that was done previously. And this brings us to another research direction of increasing the size of this dataset, maybe having more prompts or more categories. These are some of the references that we have used for our task. I'd like to thank you all for listening to us.